of a 4-day workshop for HPC Python. And by now, I hope you have learned a lot about how to create your environments, how to work with GPUs, how to load modules. And there was like a lot to cover for this Python workshop. So let's begin the last section, which is machine learning and deep learning, and how to run your machine learning, deep learning stuff on these HPCs. I am just looking at the list of participants for today. I see Dadil, Cosmos, Tetralith, and a few more who have not named themselves with their HPCs, but that's fine. Okay, so let's quickly do like 7 or 8 questions of machine learning, deep learning related quiz. And it's okay if you do not know much about machine learning, deep learning. This is a very general quiz. And while we are doing this section of machine learning, deep learning, you will learn about these things. So I see that 4 have joined, and please respond to this quiz. Question is, which tensor data type is generally preferred for improving performance while maintaining reasonable precision on modern accelerators? Modern accelerators can mean A100s, H100s, L40S, things like that. So basically, which have like latest CUDA capabilities. And it's okay if you do not know the answer, just reply to one of the answers here, and we'll see. Three have responded out of 7. We need to quickly go through this quiz, so just quickly like respond to any of the ones that you feel it's the correct one according to you. So more than 50% have responded. I'll move on. So BF16, which is brain float 16, is the one which is having a good performance on modern accelerators. And most of you were correct about it. Next question is, what is the primary purpose of maintaining a requirements.txt or environment.yaml file? Is it to speed up modern training? Is it to visualize the dependencies? Is it to ensure reproducibility of the environment? Or is it to reduce the memory usage? Okay. Right. More than 50% have responded. Let's see. Yes. Most of you are correct about it. It's to ensure reproducibility. What is the common issue when working with small files? Actually, many small files on HPC systems. What is the common issue? What's the most probable issue which arises? Is it to like it increases the GPU memory usage? Is it faster with data loading? Is it reducing the CPU utilization? Or is it hitting the input-output operations limit on the CPU or the GPU or on the whole system? The storage as well. Okay, so most of you have given an answer, which is the correct answer, hitting IOPS limit. Next question. Why should you begin with smaller batch sizes and sequence lengths? So those of you who have used like deep learning models, like text models or even vision models might know why should one begin with smaller batch sizes or sequence lengths. Okay, most of you have responded. I'll show the responses. To quickly identify issues and reduce debugging time, that is correct. Towards the end of these, the question is, why should you avoid storing large caches in your home directory? And large caches can come from Hugging Face home or Conda packages or something else. So why should you avoid these large caches in your home directory? Okay. Let's see what people are responding. Home directories often have strict quota limits. That is absolutely correct. And that's why you should avoid it. What is a recommended technique when your model does not fit into GPU memory? What is the recommended technique when your model does not fit into the GPU memory? What should you do? Should you increase the batch size? Should you disable the logging that is happening? Should you use some technique for gradient accumulation, or should you just switch to CPU training? And most of you have responded, which is correct. Use gradient accumulation. And I think this is the last question. Why is checkpointing important in HPC jobs? So if you're like training a model, you might be storing them like intermediate checkpoints. Is it to improve GPU nodes? Okay, most of you responded. Let's see. It allows recovery from interrupted training. That is absolutely correct. Most of you have responded. This is I swear that this might be the last question. What is the purpose of using tools like torch.compile and PyTorch? And those of you who are not using PyTorch, maybe you're using TensorFlow. There is also an equivalent the function to do this. I'm forgetting this. I've written it in the documentation. To speed up model execution, that's the right answer. Okay, thank you so much. Now let's move on to the section machine learning and deep learning. And most of you already know the answers to these things. And the whole purpose was for you to know that what are the good practices to deploy when you are running your machine learning or deep learning models on these HPCs. So we'll be covering three major libraries: the scikit-learn, sklearn in short, PyTorch, and TensorFlow. Now I know that most of the tech community have switched to PyTorch now if it comes to deep learning. And sklearn or scikit-learn is still a very major player when it comes to like classical machine learning applications or just data exploration purposes. So quick comparison between these three, if you do not already know this and you've not been aware of these, as I said, scikit-learn is mostly for traditional machine learning applications, whereas PyTorch and TensorFlow is for deep learning and neural networks. Like scikit-learn, I guess, came before these two, and it has been well developed by the contributors, by the community, and it has an extensive amount of resources and documentation. If you have been like aware of like these Google competitions like Kaggle and others, they were mostly done with like this library scikit-learn and others. Whereas PyTorch TensorFlow picked up later, TensorFlow being the first one of the libraries which were picked up. But unfortunately, it did not get too much of community support. PyTorch did. And lately, we can see people moving to PyTorch. Although if you want to still deploy things on edge, I still see people using TensorFlow for those reasons. It's a little bit slightly bit complicated to use its APIs than PyTorch. Okay, depending on which HPC you are on, you might be encountering these PyTorch and TensorFlow libraries in various modules. So for example, if you are an HPC2N, you'll have to load certain other modules like GCC and OpenMPI before you even load TensorFlow or PyTorch. Whereas on C3S, and UPPMAX, you can load them independently. TensorFlow, PyTorch, these are the versions that are currently readily available as modules on these HPCs. Bianca users still stuck with like old Python modules. So it's like 3.9.5 Python version, which is having some of these libraries. If you're from C3SC, then you can also find PyTorch bundle, which is having Torch, but I think it has this torch, but with that, it's also having torch vision and other complementary torch stuff in the PyTorch bundle. Similarly, Lunac also needs you to load certain other modules before you load TensorFlow, like GCC, Python, and SciPy bundle. Then you can load this. You don't need to load scikit-learn to load TensorFlow, by the way. NSC tetraathletes users are stuck with just creating their own virtual environments. And so have PDC, they have apptainers. So you can load a Singularity apptainer like this, and it has certain PyTorch TensorFlow modules, although they might be not the latest versions. But again, I think most of us, when we are actually working on our projects, we tend to create our own virtual environments, whether it's a Conda environment, whether it's a Python virtual environment, or if it's apptainer, Singularity apptainer container, where you have various libraries along with PyTorch, TensorFlow, scikit-learn, etc. Often than not, you'll also need Jupyter to run if you have Jupyter notebooks. So you might also need to load a Jupyter module if you're using just modules, or your virtual environment should have Jupyter in that case. I've listed some basic PyTorch TensorFlow machine learning examples here. And if you're interested in some advanced stuff like how to deploy your models parallelly on multiple GPUs, whether it's in the same node or across nodes, you might have to look at some other techniques, the most common one being the data parallelism. And then comes pipeline parallelism, tensor parallelism. Scikit-learn also allows for parallelism, but you might have to check whether you're able to like have multiple threads in your CPU to even work with that. Okay. Just as it's on a glance, we can see that these are like various HPCs and what modules do they already have on them. So if you're a Data user, you'll have to load this module CrayPython in order to load SciPy, NumPy. And for TensorFlow, you'll have to have the PDC module along with the Singularity module container, basically. Similarly, tetraathletes users will have to load build tool, easy build, followed by GCC, followed by matplotlib in order to load matplotlib. In the subsequent exercise that we encounter for scikit-learn, PyTorch, and TensorFlow, you are free to use either modules or the virtual environment, although I would recommend working with virtual environment because often than not, when your dependencies grow bigger and bigger, you will eventually have to switch to an environment. For my like the demonstrations that I'm doing, I will be on Alvis, by the way. And for Alvis, I'll be using the Open on Demand, which I already have opened up here. And I have one T4 in that Open on Demand node that I'm working on. So you can also get one interactive session on a GPU node if you can, a very small one, T4, one T4 is enough. Or otherwise, you can work with CPU also. Scikit-learn exercises will work on CPU very well. So let's begin with scikit-learn. Just to give like a structure to this whole session, you will see scikit-learn followed by some examples, then exercise, PyTorch, TensorFlow, a little bit comparison here, followed by examples, some tips and tricks, and then exercise. And finally, some more examples, and then some more exercise. These are some exercises that you might just try by yourself, or examples that you might try by yourself. Okay, coming back to scikit-learn now. Does anyone have any questions related to the modules that we just looked at? If anyone does, they can just either write it in the chat or they can raise their hands. So scikit-learn, I've already said a few words about scikit-learn. I think this was also one of my first libraries that I was working with when I had to develop some projects, do some data exploration. And it comes like with tons and tons of good functions. And it has been like improved in the backend. Like the functions remain the same, and then still they were trying to improve the efficiency of those functions. So if you look at the components that scikit-learn provides, there are these few components. The estimators, the transformers, pipelines, datasets, model evaluation, and parameter searches. We'll be just quickly going through these things. I'm not going in deep with them. But most often, like the main cores are like the estimators and the transformers, and probably the model evaluations. Sometimes it's parameter searches also. So these are the basic algorithms that you need to use, the estimators, for classification, regression, and clustering purposes. So if you're from like data mining background, you might be using them a lot. Uh, as simple as like linear regression or k-means clustering or k-nearest neighbors, k-nins, or decision trees are available in estimators. And they use a method called fit function, to fit onto the data set. Then comes the transformers. These transformers different from the language model transformers. They were named before those transformers. But the idea is to like transform your data and understand the features. So they come with a function called .transform. And you will see that fit and transform are used together. So you will try to like understand your data and fit your model on it. So these comes with really nice functions, like just to do scaling, simple scaling, or to understand the principal components of your data set. We'll be talking about PC and dimensionality reduction, which comes after this. Anders will be there to explain this more. Or things like TF-IDF, vectorization. If you're from like natural language processing background, you might want to like count the number of terms, inverse document frequency, and all that. Pipelines is a neat way to like stack these functions all together. So it becomes like a one linear pipeline. So you can have scaling, then you can apply linear regression. You might also want to apply multiple transformations before you put that into an estimator. So you can use pipelines for that. Looking at this pipelines also, like if you are aware of Hugging Face, they also created these pipelines in their libraries. So yeah. Data sets are available data sets, like very basic hello world kind of data sets with machine learning stuff. So iris data set, handwritten digits, Boston housing pricing data sets. These are already available. So you just load iris, and it imports the iris in a good data set form. So it's like a hello world kind of data sets available. Then lastly, the model evaluation and the parameter searches. Of course, you would like to evaluate your model. So there are various matrices with which you can use You can apply that evaluation, accuracy, FN scores, regression errors. So you can use the sklearn matrices, model selection and neighbors. Like the matrices is the main one, of course, for model evaluation. So you see, you create a model as this, the KNN, the classifier, and then you fit onto your training set. Then you do some predictions with your model, and then you calculate the accuracy with the predicted values and the ground truth values. And finally, some searches to do some, hyperparameter tuning. You have grid search CV, random search CV, or Gaussian. I think there's also Gaussian way of searching your parameters. So you can also use that. And how many folds you need, like 5 times iterations, you can also do that. These are some very basic examples to do linear regression, KNN, and decision tree. As I was already saying, like to create a model like this, fit onto your data set, training data set, make some predictions. Want to plot them, you plot them. Same with KNN. Create your model, uh, initiate your model, saying that you need 3 neighbors, you need to check 3 neighbors, fit onto your training set, and do some predictions. Similarly, decision tree, the classifier, fit onto it, do some predictions, do some accuracy, calculate the accuracy. As simple as that. So we have the first exercise, and in your exercises folder, day 4 MLDL, you will find IPyNB notebook, which is called Titanic sklearn. So I encourage you to run that Jupyter notebook. Either you can take a GPU interactive node, or you can work on the CPU interactive node. It'll be better if you're on an interactive node, not on the login node for this particular exercise. And try running Titanic sklearn with that. It uses a directory called datasets to import some datasets. So it's already in the exercises folder. You just log into CD into your exercise folder, and you can just run your Titanic sklearn.ipynb. Can I get like a show of hands or maybe some reaction to understand how many of you are going to try this exercise? All right. So let's wait for like 5 minutes. And I've already done this, so I'll go through this after you all. Like out of the bat, you might notice that the instruction says load the correct modules that contain scikit-learn, NumPy, Seaborn, Pandas, Matplotlib, and Jupyter. Depending on which cluster you are working from, you might not find all these modules. like tetralith might not. So please create a environment where you just pip install and all of this. But the names are this: scikit-learn, numpy, seaborn, pandas. It barely takes like 30 seconds to 30 to 40 seconds to pip install these. Or if you already have an environment, you can pip install in that, a virtual environment. Cross means you're stuck, or is it moving forward? Can you maybe you want to type it on chat? Or you
I'm
can speak.
stuck. Same spot as
Yeah.
Sergey.
Okay. All right. Let's look at this then. So I am. You can see my screen well. Try to make it bigger. Not able to make this bigger. Well, I'm on Alvis through OOD. I have an interactive session. And you can see that I'm currently in the exercises folder, day 4 MLDL. I copied it on my own like name, Jayant, but yeah, you can also copy exercise if you've already been doing it. So the first thing would be to, second, maybe I've already this, yes. Yeah. So we need to have an environment. So for that, we need to first load Python. So I load Python like this. Then I do Python -mvenv, followed by, let's call it test env. I create a virtual environment, test underscore env. And now I activate it. So source test bin activate. I activated the environment. Let's check if I'm in the correct path. So if I do which Python, it shows me that it's running from the test env environment. So that means I'm at the correct place and it has been activated. Test underscore env. Okay. Now I need to pip install things. So pip install. Let's go back. Scikit-learn, NumPy, Seaborn, Pandas. I copy all of this. I'll paste all of this. This remove and commas. Okay, pip install everything is the easiest way to create a virtual environment. So meanwhile, it's installing on the other environment. I'm going to just start my other environment, which already has all of these things installed. I mean, it's almost like 50 out of 111 libraries are already there. Maybe we can just wait for this to complete. I don't know. 55, 60. Oh, no, let's just wait for this. So Sergey or Frederick, can you tell me if you were able to successfully have these libraries in your environment? Oh, it's not happening. And why is that? Do you know, was there an error or was it some issue? You can write it in the chat if you wish.
I think I need to go back to some lectures to repeat them. Some basics from previous days. So it's
Well, all right. Frederick, what about you?
Currently trying. Packages installed.
Okay, you were able to install them?
Yeah.
Okay. All right, then. So let me just source activate my other environment, which already has all these things. Okay, this is already done. So let me just move back to this one. I can CPIP list should show me things, which is the environment, like the libraries that I just installed. So let's fire up Jupyter Notebook. Jupyter Notebook, IP 000 without browser. And gives me a URL. So I'll just copy this URL and open it on my Firefox that is available here. And there you go. So I'm able to run my Jupyter Notebook here. Titanic, sklearn, and that's it. Simple as that. I'll hit run, restart. So it will try to run everything. Now you might see that if it's getting stuck saying it's not able to read the CSV, it's not able to find it, just check where you're running the Jupyter from, or you might just want to change this. You can give it an absolute path to the data sets. And by the way, the data sets are here. Looking back at the terminal, there is a data sets directory here, data sets. So because Titanic's sklearn and data sets are in the same directory level, you can just give data sets Titanic train CSV, and it runs like this. So let's just quickly see what's happening inside this. This is again a classic machine learning problem. Titanic, to predict how many survive based on their features like what ticket they purchased, what was their gender, what was their age, if they had siblings, which cabin they were from, which port they came embarked from. And all of this is used using like pandas, numpy, seaborn, a little bit of matplotlib, and of course sklearn. So first things first, we load these libraries using read CSV, which is a pandas function. We plot these to see that some correlation happening. So this is just a table which we just plotted, printed. We then plotted the embarkment versus survived. So if they've been, we can see embarked from the seaport, there have been more survivors. And similarly, survival versus which class of ticket they bought. So if they were from the first class tickets, there were more survivors there than the third class cheaper tickets. Then we analyze some the features that are available. So just for the sake of it, we see the mean, median, mode values and some quantiles for the fares that we had. And here we try to like create classes for these pairs. So we created like 4 classes for these pairs, 1 quantile, 4 quantile, 2, 3 quantile, like that. And we also give like numbers to these IDs and survivors, 0, 1, 0, 1, like that, instead of saying no, if they survive. And then we plot them again. Again, we can see some correlation with the fares versus the survivors, the cabin versus the survivors, the age versus the survivors. So the seniors were the most survival, those who survived the most. Babies survived the most, again, both male and female, things like that. We can do some feature encoding, which basically means instead of having all these texts in these fields, we can have for male, female, we can have like again 0, 1 or 1, 2, things like that. So we do that. We do a feature encoding. So everything is in numbers. Then we have our data set ready to be split. We do that into 80 and 20. 80 training, 20 test cases. And then we use a random forest classifier. We use sklearn for this. So we create some parameters for this random forest. We ready our score matrix. And we used grid search CV in order to do this multiple times and find the best parameters available, because the parameters are in like a list form. So we do not know which one are the best ones. And then we fit our function, the classifier function, on our training set. So it finds the best combination. And then we can do some predictions based on the test set and create an accuracy score. So we get almost 83% of accuracy score with our classifier. Then we can validate our model using k-fold cross validation. So these are some techniques to like cut the training test set multiple times and iterate them with the model and see whether different combinations of training test set are how are they working, and just do a mean of those so that we get the actual some better like normalized score of the accuracy. So 81% is the final score. And then we can just run our predictions over this trained model. So this is how you can use the sklearn library. And now we'll start with PyTorch and TensorFlow. The sklearn did not use any GPU, by the way, because most like sklearn usually uses CPU or multi-threading at most. For PyTorch and TensorFlow, we'll use GPUs. But just let's have a look at the like a basic structure of how, if you want to compare these two libraries. As I said, PyTorch has been refined a lot by the community. So the same stuff that has been done by TensorFlow is done a little bit more elegantly in PyTorch. But the basic structures like remain the same. So you have something called as tensors that you can create, torch.tensors. Similarly, on the right side, TensorFlow has tensors in the form of like TF variables like this. And you can also tell the library that whether these tensors, which might be like weight for a model, will they be used for gradient descent algorithm to update for updation purposes. So you can say like required grad equals true. And similarly here, you can do something like this. It's by default actually true in this case. Otherwise, a variable, I think, is used scale or something like that for non-gradient ones. Then if you want to like create layers for your neural network, you can have some function like .linear in this case. TensorFlow, whereas TensorFlow is like sort of a wrapper around an older library called Keras. And Keras used to be the one which was used for creating neural nets. So it's still dependent on that. So tf.keras.layers.dense, and then you define how the dense layer looks like. Yeah, so the df constant was the one which was without the gradients. It is df variable is the one with, if you want to update the weights gradients. Then there are so many optimization like algorithms, in this case, just showing stochastic gradient descent, LR learning rate with 0.1. Similarly, TensorFlow can have something like this, again in Keras optimizers line. And then you can perform a backward pass onto your neural net to update your gradients. Whereas here you will have to update the gradients like dot apply gradients like so, and compute them like so. And that's pretty much it. This is like a very, very basic comparison between how these functions might be looking like for PyTorch and TensorFlow. And now we'll again run a very classic hello world example for TensorFlow PyTorch. It's the MNIST image classification. It used to be for, like in this case, we are using the fashion MNIST. So what you have as a data set is like a bunch of clothes classified as whether it's a sweater, whether it's a shirt, t-shirt, or it's a pant or things like that. And then the model will try to understand the features of these images, and then it will give the output whether the test set has what kind of clothes is it looking at. So someone is asking a question.
Yeah, hi, Jayant.
Yeah.
So I had a very basic question. It's like when you were putting all the modules and Python and creating environment. So can we do it directly here at the interactive session? Like we can add cells before, like the previous exercise, we can add certain cells and can we import directly from there?
Sorry, I'm not getting it. Which cells are you talking about? Like Jupyter cells?
The last exercise when we started.
Yeah.
So it started from the calculation, but we had to go to the command line and import all the modules and create an environment. So can we do that same thing in interactive session, or is this the only method we have to do?
So, okay. So do you mean like you can also in pip install, you need those libraries, right? So you can pip install those libraries right inside the cells also. Like you can just showing here, you can have ampersand, sorry, not ampersand, percentage sign pip install. Not Jupyter, of course, you need the Jupyter to be doing this, but maybe you need NumPy after this, so you can do NumPy here, pandas, and maybe you don't have all of this. So then it will pip install it for you, and then you can start importing these libraries and work with it. Yeah.
Okay, that was the basic question. Thank you so much.
Yeah. This sorry, again, its percentage sign can also be instead the exclamation mark. That also works.
Okay.
Right. Thank you for asking that question. Okay, so now we're going to run another example, which is the MNIST using PyTorch or TensorFlow. PyTorch is self-contained, but for TensorFlow, it requires utils.py also. All of these files are already in the exercise folder. I can show you again. So PyTorch _mnist.py and def _mnist.py. These two files are already there. So try, and utils.py is also there. So try running whatever you feel like running, which either it's TensorFlow or PyTorch. You can ignore these other files which I just created for the demonstration purposes, the environments that I created. But these files are already in your data set. in your day 4 MLDL folder directory. So give this a try now. Just like sklearn, you can pip install Torch for PyTorch or TensorFlow for TensorFlow if you're trying to run this one. And since this is not a IPyNB file, this needs to be submitted as a batch job. So the batch job, depending on which cluster you are on, is already given here like this. If you go below tips and tricks here in the exercise folder, this is the same exercise which we are talking about here. So try and run the either PyTorch TensorFlow code for fashion MNIST dataset for submitting a batch job. The data stored is here. And you might need to be on a GPU node if you can. Otherwise, CPU might also work, or at least for Torch. You need to pip install Torch, Torch Vision, and Jupyter for this. You already have Jupyter. You don't need that. But Torch. Actually, you don't even need Jupyter because there's just a py.py. And we'll take, we have a break right after this. So I'll let you all work on this exercise. And after that, we'll be on a break from 2 to 2:15. And then we'll come back and look at the results. After that, we'll go through the tips and tricks that the questionnaire that we had earlier. And just glance over some miscellaneous examples. So please try this exercise again. And if you have any questions, I'm here. And after that, we'll be on a break. We have 5 minutes for this again to run this. But of course, this will take some time to install. So at least let it go, let it install over this break. You can until then pip install things. All right, welcome back after the break. Okay, so let's look at our PyTorch example for MNIST image classification. So there was this one Python file with PyTorch in it, and we were supposed to submit it with the batch script, simple batch script. So I'm on C3SE Alvis. No matter which HPC you are on, just is a matter of defining your account and the amount of time you need and the GPU you want. So for example, in PDC, you give a partition GPU. In NSC, again, you say GPUs per task equals 1 if you want 1 GPU. Similarly, on Lunac, it's a Gress flag. This is HPC2N giving GPUs equals 1 and a constraint of NVIDIA GPU. And UPPMAX has flag GPUs equals L40S colon 1 to give you 1 GPU of L40S. And then followed by loading a Python module, starting sourcing the environment that you created for this PyTorch or TensorFlow, and then running the Python script by Python, whatever the name is, if it's PyTorch _MNIST or TF _MNIST.py. So this is what we'll do here. And let me just close this one. Yeah. So we can close this one. So in my case, I have the same PyTorch MNIST.sh. This is Alvis, so I'm asking for 1 T4 GPU. Module load the Python module, sourcing the torch.env that I created, and Python PyTorch mins.py. And we give this by sbatch PyTorch mins.py .sh, and we give that to that one a node containing 1 T4. It takes like a minute or two to run this example. I have already done this, so I'll just show you the output of this. Yeah. So you can see, just glancing over the .out file, that we have run now multiple epochs, and it shows the loss reducing as we go from one epoch to the other. So it starts on 2.2, somewhere around 0.86, drops, then it runs for another epoch, and then another epoch. And in the end, we get a testing accuracy for, over the validation accuracy for 87%, an average loss being this. And we are able to predict one of the images as ankle, boot ankle, and the actual was also boot ankle. So one of the predictions was correct. Now this data set is, you can't see this data set because it's in a special raw format. So it's like a UByte format. So you won't be able to see this data set. But maybe I can Google this and show you MNIST data set fashion. How does this look like? So it looks like somewhat like this. Oh, yeah. It's like a big batch of like different clothes, including some heels, shoes, and all of that. Yeah. So coming back to our example here, let's have a look at the script that we had. So we are looking at the PyTorch script first. So we have loaded Torch and Torch Vision for our purpose. We are loading the MNIST dataset like so, and this can also download from the URL, but we are already giving it the dataset path that we have with us. And then we create a data loader class for a training and test set, and we fix a batch size of 32 in our case. Okay, and we print out the shapes of the input, and we can see the height, weight, number of channels in the output file here. So we print this out like this. So 32 batch and only one channel, 28 by 28 is the size of the image. And the prediction is just like one prediction. So it's going to be, it's going to be like as many as the number of images in one batch, which is 32. For this purpose, we have defined the device as CUDA. If it's available, then it will use the CUDA, which is the NVIDIA. Otherwise, it will run on CPU as well. So you can run this example on CPU also. Then we have a class of neural network, and it's a very basic neural network with just one hidden layer. The input is 28 by 28 as we saw. The hidden layer is 128 with 128 weights. So the input layer is like 20 by 28. We compress it, we make it 128, and then we compress it to output of 10, because there are 10 classes only. And in between, we have activation functions, which is the ReLU functions here. So we can stack them all together with a sequential function. And we can define, okay, one linear layer followed by an activation function, linear activation, like that. So this is how we initiate it. And then we define a forward pass function. And it will calculate the logits of these for each 10 classes of all of these 10 classes. We load this neural net onto the device, and we define a loss function, which is a cross entropy loss function. And we are using the Adam optimizer for this with the learning rate set to 0.001. Then we have a training and test functions. So for training function, for each batch, we load them onto the device, the image and its output. We pass that image, the input. We do some prediction. With that prediction and the ground truth, we calculate our loss using the loss function. And after that loss has been calculated, we do a backward propagation to update our weights of that neural network. So we step through our optimizer, Adam optimizer. And then we calculate the loss. For test also, we'll do something similar. We are calculating the number of batches we have for the test set. And we are again loading the image and the output to the device. So we can calculate the difference between the predicted output and the ground truth. So we pass that through we calculate using our loss function. We get the losses, and we can calculate how many of these were correct. Those were the correct ones will be counted as 1, and otherwise they will be 0. So we calculate the number of corrects, and we finally calculate how much we had and how many of these were corrects, and that's how we calculate the accuracy. So we run this 10 times, and we have our classes defined, the 10 classes, and we make a prediction on one of the classes. So we just pick up one of the images from the test data set and its label, and we make a prediction. And this is what we see here after running the epochs, which were like for 10 times, and showing the accuracy here. Make a prediction for one of the images and its associated actual ground truth, which matched in our case. Okay, let's look at the important part, which is the tips and tricks here. And these are the lessons learned, which I learned personally, but also we usually see people making mistake when they're running their machine learning or deep learning projects on any of these HPCs. So first thing is to understand your data. That is important, because if you're not making sure that your data type is the correct type while you are processing it, you might maybe bloat up your whole model, and that might reduce the memory footprint that you have available on the GPU device. So you should know which data type your input is available in, and in which data type you want to be processing your inputs. So BrainFloat 16, FP16, FP32, FP64, is it enough to just work with like a lesser precision value than to run in a 32, let's say, full precision, it's called in machine learning terms. The latest accelerators have a capability to also run TF or BF16, which has lesser precision, but the size remains the same. Then it's the version management. Always have like your requirements.txt, environment.yaml, or PyProject YAML, something like that. Like always freeze your dependencies once you have sort of developed your model and you're just running predictions over it, or you know what kind of environment you need to replicate this. If in case something happens, something breaks down, you can always do that. So do freeze your dependencies, which means also freezing your versions for these libraries. Then, as I said, document versions, and keep your things away from home directory as much as possible, because many times, like even if you are using IDs like VS Code, even if you're just running your models, it will definitely create a lot of temporary files which might bloat up again the home directory. And that can create like a lot of small files on your home directory, and usually that has a quota limit. So you might hit that. But if IOPS are important for you, you want the creation, updation, deletions to be very quick, then it makes sense to be on your home directory. You can also use the temp folder for that particular node that you are running on, or the scratch folder if you the scratch directory if you're running on a particular compute node. This is also mentioned here in the optimize IO operations to use your scratch storage or temp storage. Like even if you're like installing things at pip install, it will download things, it will try to install things. If you're doing your apptainer work, creating your app containers using apptainer, then also. Whenever you're starting your model creation and you do not know where to start, you always start small. So start with smaller batch sizes and smaller sequence lengths. See what's working for you, what's not working for you, and only then you can scale it up, because you can always scale it up to many GPUs. But start very small and make sure that you have understood your architecture well, and then you can create bigger batch sizes of if you want to for your input data set. This, of course, reduces the debugging time later on, because otherwise it will take too much time to just run. And you can also monitor your memory usage easier, and it also always like helps reduce out of memory errors on your GPU. And coming back to the IOPS. So having a lot of small files will easily hit your IOPS limit. This is a sort of also a downside for having a distributed storage system, which HPCs usually do. So if you want to, you are creating a lot of small files, either you try to bundle them together, zip them together, or you define where they are going properly. Then you can avoid these bottlenecks. You can also use specialized data formats for handling these files for machine learning, like HDF5 or Arrow files, Paraquet files. These are common file formats that people use to manage these small files, or even one big file, or checkpoints of their model. And as I mentioned, that you can always store your images or a data set into a temp folder or a scratch folder or your temporary files while you're doing pip installs and things. Storage management, again, is a thing to emphasize again. Always keep monitoring your quotas on your storage. And it doesn't just mean the file storage space, but also how many files can you accommodate in that storage space. Consider using compressed formats, again, like zip, or specialized formats like HDF5, Arrow, and properly define your directories, like the environment variables for these files, HF home, if it's Hugging Face, Conda package directories, and all that. You can also remember to like clear out your files after you are done, or just not store them right after you done installing things. So pip, cache purge, conda clean, all these will be helpful when you're trying to clean these files. The GPU memory management. So, GPU memory is one of the bottlenecks with when you're working with deep learning models. And so you should be monitoring these memory just with basic things like HTOP, NVIDIA SMI is almost available everywhere. You can have a look at it and see if your GPU is, how much memory is there. And always try to remember, if you're using PyTorch, TensorFlow, these libraries, always try to reserve a little bit more than it requires. So keep that in mind when you're planning on putting on a model on one of these GPUs. Then, especially for PyTorch, there is this URL, which is the PyTorch memory viz. You can't see anything right here, but it's empty for now. But it allows you to drop files here. And with that, what you can do is, let's say you're running a model and it's training. It has trained. So you want to see which sections of this model took the most memory in your GPU. You can create a pickle file, for example, for this. And you can just Google how to create a pickle file or monitor the memory of this model. And you can drop it on this URL. It will show the breakdown of each tensor of that model, which one of the model at what time was taking more memory. There are also specialized tools for this NVIDIA Insight tensor board. Maybe you might not even need all of this. A bit complicated to work with if you're a little bit new. But start with HTOP and NVIDIA SMI. So again, let's start small with smaller batches to avoid these out-of-memory errors. Use techniques like gradient accumulation if you're doing some fine-tuning or training. This will allow you to limit the amount of gradient updates you're doing at one time of the weights of the models. Then there are techniques to also train or fine-tune the model in a mixed precision way. It might start with some precision, then it might go to another precision, and then as it outputs, it might turn into some other precision. So these mixed precision trainings are also available. PyTorch provides some functions already to do it if it's possible for that GPU. Autocast is one of those methods, and for TensorFlow, Keras, mixed precision is that function. And this set of LLMs, you will have to sort of know if you will be able to fit your LLM for inferencing or fine-tuning purposes. So for inferencing purposes, math is a bit simple. The number of parameters that the LLM say it has, let's say 3 billion. And for each parameter, what is the bytes it's stored in? So let's say it's stored in TF16 or BF16, things like that. So you can multiply that 3 billion times number of bytes it has. And you should also have 1.5 times an overhead factor just in case, because it depends which library you're using for inferencing. They will also take up some space. And while you're doing LLM training or fine-tuning, not exactly training, but fine-tuning specifically, whatever the inferencing was taking, multiply that by 2.5 to 3.5 for an overhead factor. And this depends a lot because, which method you're using for fine-tuning. It's LoRa, QLoRa, and other methods. So it might depend how many gradients are getting updated, how much is the optimizer states taking space. Now, if you're wondering how I got these numbers, it's I think it's mentioned somewhere in Hugging Face documentations. This is what they recommend sometimes if you're trying to do fine-tuning your language models. Important factor is also to do job monitoring. So I use Tmux a lot. So use Tmux if if you're running a Jupyter notebook, use the Tmux before that and run it in a window. and then switch to another window in the same session. Do logging as much as possible so that like you know where it's failing, what's wrong. And also happens that sometimes the admins also terminate jobs if something is wrong on the clusters. So at least you'll be safe from that. Checkpointing is also important if you're doing training your models. Put timestamps in them so that you know what went wrong at what time. You can also share these logs with the application experts like us to also help you out in that case. Then there are some GPU or performance optimization like tools that you can also use. So one of them was NVIDIA Insight that I mentioned here. PyTorch also helps you accelerate your models. So it compiles it before it runs it and provides a function.compile model. So it becomes much faster to train your models in this way. But of course, it's not available in all the GPUs. It depends on what GPU you're using. So Ampere and above, you can do this. But then also it requires some other kind of libraries, might give you errors otherwise. Optimize data loading operations to match your GPU computation. So, maybe your GPU is taking too short for computations, but most of the time is just going into data loading because the CPU-GPU communication is slow. So I try to understand what bottlenecks is so that you can improve your performance. And benchmark to find optimal batch size. It's not always true that bigger batch size or very small batch size is the optimal one for your GPU, because GPU has a tendency to coalesce its memory and load them all together. So try to fill with the batch size just to know which batch size is optimal for your hardware training. Okay. So with that, I have covered most of the tips and tricks and showed you one example of MNIST, image classification. This exercise is the same one which we did. I would like to know if someone was able to run it or tried it. Can you give me a reaction? Meanwhile, there's some miscellaneous examples that you can also look at. So this is basically if you're trying to do hyperparameter tuning, or you want to run with different parameters to understand which parameter is the best. Simplest way is to just run the same model multiple times. So you can create a Python file which has arguments like parameter 1, 2, and so on. And you can give it into output its standard output into a file. You can do this multiple times while you're on the same node. So this is the basic way to start with running several jobs and in the same model with different parameters. So this was an example with scikit-learn and TensorFlow. You can try it by yourself. Mind you, this will download a data set from Ionosphere CSV data set from the internet for this to work. And lastly, there was additional exercise, which is just fitting a polynomial function, a sine function, onto a data set. This is also given, and you can run exactly the same way we ran the MNIST data set. You can also run this one. I have done this before, so I can just show you the output. So nothing much going on. It's just a bunch of input and output, at this x-axis, what was the y-axis? And then you try to understand what's the polynomial function for this x and y coordinates. Okay. So with that, we saw three major libraries: scikit-learn, PyTorch, and TensorFlow. And whenever you do not know you're stuck how to load these libraries, you can always do module spider and understand what were the libraries that are available and how to load them. And just remember all these tips and tricks. You can always come back to these to optimize your pipelines, machine learning pipelines. Okay. Is there any doubts, any questions? If not, we'll be going on a 15-minute break. And when we return, we'll have Anders Haas. He'll be talking about dimensionality reduction. And he is from research infrastructure called InfraViz. And he'll also talk a little bit about what InfraViz is and how researchers like you can take help from them to do visualizations if your project requires you to do visualizations. All right, so we are going on a break, 15-minute break, and we'll be back in 15 minutes at 3.